Good day, everyone. Our project title is Improving the Performance of Online Predictive Modeling of the Thermal Effects of Bioimplants. Our team consists of
Michael Goldstein,
Nikhil Patel,
Solomon Martin,
and Alex Zhu. Our faculty advisor is Dr. Ying, Zhang, and our PhD advisor is Ayça Ermiş. Implantable biomedical devices are getting more and more attention around biomedical situations. They have been known for monitoring important vital signs and also injecting treatments when necessary. However, any medical implant capable of carrying out non-trivial missions would contain complex circuits. Continuous operation of those circuits would induce excessive heat dissipation. Such heat dissipation is a problem since many sensitive organs, for example our brain, can only take a maximum 0.8 degrees Celsius difference. Therefore, it's important to estimate the change in the temperature of such device. Since the temperature is such a complex system that accurate modeling based on physics and material science are often very hard. We use a system identification scheme to estimate and predict the temperature of one such system, and we seek accurate prediction to avoid detriments. The current prediction algorithm has a spatial data and non-spatial data section, as the system contains more than one sensor distributed across different sections of the device. Solomon will go on to talk about our objective given this background.
As Alex stated, our main goal is to accurately predict heat dissipation through system identification methods. More specifically, we seek to improve upon an already established prediction model. The base model converges to reasonably accurate predictions in about 500 seconds, but for the intended application, it's important that we minimize the convergence time. The model that we are building upon involves two major components, the spatial and the non-spatial, as shown by the two major branches of the algorithm depicted in Figure 2. The non-spatial component finds a general prediction at the origin of our test space, while the spatial component determines how that prediction value would vary in space. The proposed improvement methods involve implementing alternative RLS filters for the non-spatial component, applying different kernel models for the KRLS filtering in the spatial component, modifying the sensor weights matrix, refining the preprocessing, and more accurately defining the physics-based COMSOL model we are using for testing. The initial solution for improving the convergence rates of the RLS filters within the overall model was to apply fast transversal RLS, or FTRLS, in place of those filters. We sought to use this solution due to the decreased time complexity with respect to the filter order M. FTRLS filters have a big O of M, while RLS filters have a big O of M squared. While working on applying a multiple input version of the FTRLS, we found that the algorithm had an inherent positive feedback mechanism that was causing internal instability. To mitigate this, we first attempted to normalize the recursive variables, and later shifted to applying an error redundancy scheme. By arriving at the errors in multiple ways, the intent was that we could stabilize the error that was the source of the filter's issues. This did not work as expected, however, and we determined that there was a conflict of application. The FTRLS basically did not fit our estimation problem. So we pivoted to fast array RLS, which is better suited to our problem.
Another solution would be the use of kernel functions. In a nutshell, kernel functions remaps the input data into a higher dimension so that it might provide better linearity. Figure 3 is a showcase of kernel function in operation. When data are distributed as shown in the middle graph, a criterion to separate the dataset as simple as that of the top graph is no longer a viable option. However, if we apply a kernel function that, for example in this case, y equals x squared, we can clearly define the straight line that separates the two different types of data. While we do not seek data classification, a dataset situated better in linear fashion helps the prediction algorithm update its weights. We also recognize that kernel functions could be parameter sensitive, so we are also looking into automatically adapting parameters for kernel functions. In here, we try out two kernel functions, vector norm and Gaussian vector norm, which are norm and its Gaussian distributed counterpart of the difference between input data and dictionary vectors. Dictionary consists of inputs that when prediction deviates much from actual results. We add this input vector since it may show the necessity to increase the complexity of the algorithm.
Our current system uses a weights matrix generated by running a spatial autocorrelation algorithm over a matrix of the heat sensor locations. The result is a matrix that we can use to estimate the temperature differences between different heat sensors. The problem with this system is that it only predicts accurately for the sensors that are farther away from the heat sources. It basically ignores the heat sources and only looks at the change in temperature for each heat sensor relative to the non-spatial heat data. We decided to try augmenting this weights matrix using a bivariate Gaussian distribution and calculating the weight, so to speak, that both heat sources have for every sensor, and inserting these weights down the diagonal of the matrix, which is currently all zeros. The expected result was that we would see almost no change in the sensor predictions that are far away from the heat sources, and a significant increase in accuracy for the sensors that are closer.
So better preprocessing is another solution to improve convergence time that we decided to investigate. The thought behind it being that if we can format or reduce the data being fed into the algorithm, basically improve data quality, then quicker convergence would be seen. The main methods we investigated were normalization, detrending, and regularization. To give a quick summary of these methods, normalization ensures that no one parameter exerts disproportionate influence on the prediction algorithm by dividing them by some factor. Here, these parameters were power and temperature. Detrending allows us to focus on fluctuations in temperature, irrespective of the general upward trend, done by subtracting either the mean or linear fit from the data. Finally, regularization essentially tries to prevent over or underfitting by including a penalty term in the predictive equation. These techniques were already a part of the system from the start, but we wanted to check if any significant improvements could be made. I did this mainly by trying different regularization methods called L1 and L2, as well as normalization factors. Moving on, COMSOL, which is a multi-physics simulation software, is an important tool for us to get data for algorithm testing. It allows us to simulate the implantable device within any environment we model and get its time-dependent temperature. We can use these results by comparing them to what the algorithm predicts using the same set of data. It's important that this COMSOL model is as accurate as possible to the actual environment so that we don't declare success on faulty premises. The ultimate goal is to model a brain implant situation, primarily because the brain is the most delicate organ. Models that were being used previously had one main flaw. They didn't take into account the body's natural homeostatic cooling, which has a definite effect on temperatures. I tried to remedy this by editing the two existing models, starting by experimenting with the simpler one and extending my findings to the more complex. Now, let me pass it off to Solomon to start talking about the results.
The fast array RLS implementation is still in progress, however it should succeed in improving the RLS convergence rate. For one, it has the same reduced time complexity advantage that FTRLS does. However, being derived from a Laguerre model makes it better suited for our prediction problem. We can also expect more stability from Laguerre-derived RLS as opposed to the typical finite impulse response RLS, due to the fixing rather than the arbitration of the filter's poles.
For kernel RLS algorithm, here we show the prediction results of one sensor on our platform. The green line is the kernel prediction algorithm using the vector norm function, and blue for its Gaussian counterpart. The red line behind the blue and green line is the ground truth reference measurement, while the pink line is the prediction generated using no kernel at all. We can tell kernel RLSs reaches their target state within 400 measurement updates, while vector norm reaches almost within 100 seconds, while RLS produce a constant offset in prediction. We generalize the MSE per prediction in table 1, and vector norm outperforms RLSs with no kernel by 2 orders of magnitude.
The results for the spatial weights additions currently need some development. The Gaussian function is built and runs, but the values need testing and possibly scaling as well as integration into the main code.
In regards to preprocessing, what we soon came to see is that developing it further didn't really help reduce convergence time, unfortunately. Preprocessing seems to better benefit algorithm steady-state accuracy more than anything, which is an area of lower priority when it comes to the current algorithm, if you remember the graph from the objective slide. Thus, I decided to move on to COMSOL. If you turn your attention to figure 6 and table 2 on the right, you'll see the simple COMSOL model we experimented with, along with the materials it's composed of. Originally, it consisted of a chip made of silicon and FR4 immersed in a pool of water at 310.15 Kelvin, which is the average temperature of the body. What it's able to do is add cooling via flow of the pool, similar to how blood keeps the body temperature static. One end of the model is an inflow, where water comes in at 310.15 Kelvin, and the other, an outflow, where water comes out a little warmer due to the chip. Because of this, we see a much smaller delta T between the chip and the environment on average. Obviously, this isn't brain analogous, but is a step towards implementing more characteristics that are, which is a good lead into our discussion about conclusions and future work.
We can draw much conclusion from our results and project many thoughts into the future. Using the kernel for recursive least square methods clearly has its merits, and we show the rest of the sensor predictions in figure 5. It is capable of producing more accurate results that converges in a shorter time. However, it needs to be taken notice that such kernel functions often need to be engineered. They are very parameter sensitive. While one of our goals is to adaptively update the kernel function parameter, we fail to meaningfully produce one such method that updates the parameter, since the RLS cycle outside of the kernel function is also updating its way, and it is hard to conjugate those two updates. However, I believe that finding a way to auto-update kernel functions is a good future goal to be pursued.
The picture you see here is a more complex COMSOL brain model, which uses the scalp, skull, and brain biomaterials, top-down respectively, with an implant sitting on the brain. We've added flow cooling to the basic model we saw earlier, but in the future, we're looking to apply the same concept to this model, perhaps with the addition of heat fluxes.
In the future, the team should investigate integrating this new set of values into the weights matrix after testing different ways to scale the weights so that they can have the intended effect on the data output.
As stated earlier, fast array RLS is more suited to our problem when it comes to improving upon the RLS filters in the non-spatial portion of the algorithm due to the Laguerre-based definition. The next step here is to finish the implementation and compare convergence rates. Here are the references we use. This concludes our presentation. Thank you all for listening and watching.